Okay, guys, it's been a little while since I've done one of these, so let's just get right into it. So, objective number 2, which is electron notation. So that's electron configuration, orbit diagrams, all that kind of fun stuff. So we'll just kind of get right into this. Now, first off, this equation really doesn't truly connect with electron notation. In our last video that was all about light and energy and all that stuff, this should have probably been in there. So this is de Broglie's equation, which allows us to calculate the wavelength for a particle. So it helps us understand how light can behave like particles and waves, and it gives us a relation to mass. So you can see wavelength is in there, Planck's constant is in there, and then now we have this velocity and this velocity and this mass that's related in here. So it gives us a way to treat it for fast-moving particles, wave-like particles. So photons will exhibit some particle properties, but they also are waves. Larger things, like physical things that you would see, like a ball or whatever, technically do exhibit some wave-like mechanics to them, but it's not really anything that's like visible or really noticeable in any way. So for this, I mean, if we're talking about light, we're all talking about a value of c here. So that normal 3.0 times 10 to the 8th meters per second. But from there, this gets us into electron configuration. So all of this electron configuration really centers around this, Heisenberg's uncertainty principle. It is impossible for us to know the exact velocity or exact location of electron. So if we know the velocity, we can't know its location. If we know its location, there's no way for us to know either the magnitude or direction of the velocity. So basically, you just cannot know both of those at the same time. Now, chemical properties will depend on the number and arrangements of electrons in an atom. So usually only the valence electrons are the ones that we pay attention to. So those are the outermost electrons. But the electron configuration and orbital diagrams are kind of a code to tell us where those electrons are. So each chemical has its own electron configuration, and the orbit diagram is a picture representation of those different energy levels. So we'll kind of just go through some of these things here. So this right here is truly probably the best way to say here's what an atom looks like. So in the past, I'm sure as little kids you saw those fun little like planetary models where the electron kind of followed a path and spun around. The reality is it's a probability density. An electron is just going to be somewhere within this region. So we call those spheres or shells or clouds, if you will. So an electron cloud or an electron shell. It is the probability likelihood of finding an electron. Will say it's in this area. You just don't know where in that area it could be. So depending on the electron, you know, it might be right here at a particular moment and then bounce over here. And so you just don't know. It can be anywhere within this cloud. And you can also have clouds that stack on top of each other. So an S orbital is a sphere kind of probability shell. So you can have 1s shells or energy level 1 shells, 2, 3, 4, 5, 6, 7. And it is just a probability shell somewhere in here. The orbits have a slightly different arrangement to them. So they are kind of a figure 8 pattern, and they can arrange either on the z-axis, the x-axis, or the y-axis. So you can have 3 different p orientations. And then, of course, just like S's, you can have different energy levels. So those energy levels range from 2, 3, 4, 5, 6, and 7. You'll notice there is no 1p energy level. So unlike S's, it cannot exist in the first energy level, but it can in the upper ones. And again, it's just a probability likelihood of it being somewhere in this figure 8 shape. D orbitals have an even odder arrangement, so instead of being on the axis, they're 90 degrees to the axis, which gives you 5 different orientation probabilities, with this last one being kind of odd and having this weird like donut shape to it. And those all range from 3, 4, 5, and 6. So there's no 1, there's no 2, and there's no 7. And then last but not least, it's kind of hard to see it here, and I'll zoom it in a little bit here. But so there's the S shape, P, D shapes, and down here you have these funky F shapes. Don't worry about the shapes, particularly for D's and F's. They're very odd, and it's not really anything you need to know shape-wise so much. But F's, you can have 4F and 5F, and that is it. So that cuts out 1 through 3 and 6 and 7. Okay, so going back to full size here. So all of those numbers out in front, the 1, 2, 3, 4, those are called quantum numbers. They are a way of describing the energy of the electron. So something in the first quantum shell is going to be lower energy than something in the 7th quantum shell. So 1s versus 7s. It's generally notated in that, again, out in front here, so the energy level is basically describing that one electron, and what level it's at. So n equals 3 here. The quantum number is 3 because it's in the 3rd s level. Okay, and then from there, so again, quantum numbers can go 1 through 7. There are 4 different sublevels, which are the S, P, D, and F. The S sublevel has 1 orbit in it, which is this one single box, and that box can hold 2 electrons. So you can have an up electron and a down electron, which is called their spin. Don't worry so much about that, just know that in a single box, a single orbit, you can have 1 up and 1 down. So 2 electrons in 1 orbit. Whereas P's have 3 orbits, so that means 6 electrons. D's have 5 orbits, which is 10 electrons, and then F's have 7 for 14 electrons. So again, the number of orbits is half of the number of electrons that level can hold. Okay, so this gets us to the fun rules. So there's the Aufbau principle, or Aufbau principle. Electrons will enter at the lowest energy levels first. So I like to call this the concert rule. If everyone has general admission tickets, very first person in, what are you going to do? You're going to get as close to the stage as you can physically get. So you are going to try to fill in as close to the stage as you can go, and you'll fill in farther and farther back from there. So that's essentially what that principle is talking about. First electron in is going to try to get as close to the stage as possible, as close to the nucleus as possible. So lowest energy, and then you fill into higher energy levels. You'll kind of see that on the next slide, what I'm talking about and what that sort of looks like, but I like to call that the concert rule. Pauli exclusion principle. This is the up-down arrow thing. So in a single orbit, if you have 2 electrons there, so you can picture a box here as like a bench seat. So you can have 2 electrons in that one bench seat. They want different orientations though, so one wants to be up and one wants to be down. So you essentially just don't put 2 up arrows in a single box. Okay, and then Hund's rule, we can call this the bus seat rule, or Ms. Butler likes to refer to it as the urinal rule. It essentially says that if the energy levels are even, you are going to try to spread out as much as possible before you start doubling up. So if I'm filling this whole thing in? Well, I can put one up arrow here. Well, if another electron comes in, it can try to sit right here next to this one, but honestly, it's going to want to pick a farther spot because they're open. So it will fill in here and then fill in here. So you'll occupy all three orbits before you go back and fill them. So now I can go in and start pairing them up. So again, I had to occupy all three orbits before I started going back and pairing them, because you want to be as spread out as possible. If you get on a bus and you see a stranger or an open seat, do you sit next to the stranger or do you take the open seat by yourself if they're at the same energy level? Well, you probably take the open seat. Okay, so this right here is the concert. So if this is the nucleus, this is where your protons and neutrons are sitting. So the protons are the ones that are actually drawing the crowd. So we have protons here. Now, however popular this concert is going to depend on the protons. More protons, more popular. More electrons are going to show up. So if this is a concert, well, you have the stage, and the protons are up on stage, and here is the concert hall with all of the seats available. Now, just like a nice fancy concert hall, those seats are fixed. There's only so many seats close to the stage. As you can see, there's only a handful of seats close to the stage. As you get farther away from the stage, it kind of fans out, and you get more and more seats way up here in the nosebleeds. So the electron configuration is set. All of the seats exist, even if they're not occupied. So that means that hydrogen and helium still have all of these open seats, just no one's sitting in them. So they exist as a probability. It's just that no one is in that probability. Because hydrogen only has one proton, it's only going to draw one electron. So he has one fan. It's probably his mom, which is like kind of sad, but kind of cool, whatever. So like there's one fan. And so that one fan, because of the Aufbau principle, will come in and sit as close to the stage as possible. If you have 25 electrons, well, or 25 protons, you'll pull in 25 electrons. So you'll fill in up to 25 electrons, and then you'll stop. These sections right here that have multiple seats, well, they're all one energy level. So as fans come in, they don't necessarily know each other, so they will come in, and so you'll get electrons that fill these lower ones. And as fans come in and fill here, because of Hund's rule, they are going to try to occupy these seats before they start doubling up. Now here, this fan still wants to be close to the stage, the next new fan that comes in, so he's going to sit with the stranger instead of taking a farther back seat. There's nothing wrong with that, and they'll just fill in like that. So that's where all those principles come in. Okay. So looking at the periodic table, you can kind of treat it like a road map. So this block right here is something called the S block. What that is saying is that the last electron added to these elements is in these particular S orientations. So hydrogen has just the one S, helium has two S. As we go, lithium and beryllium, those are 2s orientations for their valence electrons. Their valence electrons here are 3s, 4s, 5s, 6s, 7s. So the row, the period number, tells you what the quantum number is for s shells. For p's, since those are the next ones, well, again, this is the second row, and you have 2p, 3p, it's hard to see, 4p, 5, 6. There is 7p technically as well for those brand new elements. So again, the row that this is in tells you the quantum number of the respective p electrons. So anything here, most recent electrons, the last part of their electron configuration is going to end 2p for this row, 3p, 4p, 5p, etc. Here we have the D block. As you'll notice, we have 4s but 3d. The D block is actually lower energy by 1 compared to the row it is in. So this is the fourth row, but those D's only have an energy level of 3. So they're actually kind of inner electrons for the most part. And then F does the same weird funky thing. This right here belongs right over here sandwiched between 6s and 5d, and it's only 4f. So it's actually 2 less than the row it's in, and same with this. So again, these are interior electrons. They don't have the energy level of the S and Ps. Okay, so breakdown, quick overview. S sublevels have 1 orbit, holds 2 electrons. They exist energy levels 1 through 7. Ps have 3 orbits for 6 electrons, 2 through 7. Ds 5 and 10 electrons, well, 5 orbits, 10 electrons. Only 3 through 6 because again they're 1 less than the row. And then Fs have 7 orbits, 14 electrons maximum, but only exist in 4 and 5. Okay, so draw energy diagrams. So if we have potassium here, well, we have 19 electrons. So first 2 electrons are in 1s. That orbit is full. Move to the next one. 2s, full. 2p, which holds 6 electrons. So now we're up to 10. 12 electrons for the 2 and 3s. Another 6 in 3p, so that brings us up to 18, and then 4s, which is our very last electron. So his valence electron is just this one 4s. Cadmium does the same thing. You'll notice that he fills in this 5s before he goes through and fills in 4d. So you have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10. And that's just the exact same thing I said. So basically I just took your concert seats, said, oh, here's what seats are full, and I wrote that out as if it was instructions. So 1s is full, 2s is full, 2p is full, 3s is full, 3p is full, and oh look, the last fan is sitting in 4s. Same thing for cadmium down here. This right here, the 5s gets filled before the 4d. The notation-wise, you can actually switch these around, and you'll see me do that in a later slide here. Okay, again, valence electrons versus core electrons. Valence electrons are the electrons with the highest energy level, so the outermost electrons. Core electrons are inner electrons. So going back, I have energy levels 1, 2, 3, and 4. This right here, this 4s, is the highest energy level electron, so he has 1 valence electron. Cadmium down here, well, his highest quantum number is this 5s, so he has 2 valence electrons because he only has 2 electrons that are in that 5th energy level. And then noble gas configurations. What you're doing with the noble gas configuration is you take the normal configuration, and instead of writing out everything that comes before, you just want to see the valence electrons. You just want to see, well, actually more than just the valence. You want to see just the last, most recent electrons. So what you do is you find the noble gas that ended the row before. So iodine here is in row 5. So period 5. If we go to period 4, the end of period 4 is krypton. So what we're saying with this configuration is, hey, the configuration is exactly the same as krypton, and then we're adding what's different. So from krypton, which is all the way up to 4p6, well, the only thing that's different is we have 2 electrons in 5s, 10 electrons in 4d, and 5 more electrons in 5p. If we added 1 more electron here, that would be the same configuration as xenon. Oh, look, here's xenon. So mercury, which is 1 row below iodine and a little bit to the left, has the same configuration of xenon, which has up to 5p6, and the only thing that's different from xenon is these 2 electrons in s, these 14 in 4f, and then these 10 electrons in 5d. So the noble gas configuration says, here's where we're starting, which is the end of the previous row, and here's what's different as we build that new row in. And then going through and saying valence electrons, well, highest energy level, valence and valence, so iodine has 7 valence electrons. Mercury here, well, 6 is its highest energy level, so we consider it as having 2 valence electrons. Now, it can do funky things with these other electrons, but generally we assume it has 2 valence electrons. Okay, trying to get to the end of this so that it's not too much longer. Unpaired electrons. So those are going to be an orbit box that only has 1 up or 1 down without having both an up and a down. So unpaired just means that that orbit box is not full. So there is an electron that is only pointing one direction, and that's it. So this is considered unpaired. Diamagnetic, it's where magnets go to die. They are going to be things where the electron configuration is all paired, so they are not interested in magnetic fields. So any element with an even number is going to have completely paired, sorry, actually I should be careful saying that, elements that have an even number of electrons and haven't left any spots open due to Hund's rule are going to be diamagnetic. So that's going to be anything that's filling its last sublevel. So that would be things like beryllium, magnesium, calcium, strontium, barium, zinc, cadmium, mercury, and then the noble gases. Those guys are all diamagnetic for sure because all electrons are paired up. There's also some other diamagnetic ones in there, but we'll kind of talk about those later. And then paramagnetic, those are the ones that are going to be attracted to a magnetic field. So it has 1 or more unpaired electrons. So that means it has an orbit diagram in which this is true, and you have a single electron sitting there unpaired. So they have some attraction to magnetic fields. When they're in a magnetic field, they show signs of magnetism, but they're not magnetic on their own. And then ferromagnetic, ferro meaning iron, is something that retains magnetism upon being induced to a field. So it is something that will still be magnetic after you take it back out. Really, iron is the best example of this, which is where the ferromagnetic comes from. So the big ones is diamagnetic, completely paired up, no attraction, actually slight repulsion to fields. Paramagnetic, there is attraction, so long as it's inside of a magnetic field. Okay, ground states and excited states. So ground state is the normal electron configuration. So the 1s2, 2s2, 2p6, 3s2, etc. So down below you can see the ground state for silver. An excited state is when one of those electrons picks up some extra energy, jumps up to an excited energy level, and then falls back down. So it's basically, if I kind of go back to our stage here. So again, the electrons want to be as close to the stage as possible, but let's say like you just have a fan that just gets super excited, just has all this pent up energy all of a sudden, and just decides to run out of a seat and jump up here and like has to just like dance around, find some open space to kind of just like be weird and burn off some of that extra energy, and then it comes back to its original seat. That's what an excited state is. That electron has all this pent up energy, needs to express some of it, so it jumps up to this excited place, finds some open room by itself, and then gets rid of that energy and comes back to its seat. So this is the ground state. Really, any of these electrons is capable of going to an excited state, but we're going to say it's the valence electrons, so it's going to be these guys. So these two valence electrons just can't take it. They get too excited, so they jump out of their seats and jump up an entire energy level and say, so they go to 6s. Again, those seats exist, they just aren't occupied. So something can go occupy them temporarily. So the red is the original ground state. This is the excited state saying, here's where those two electrons decide to jump up, and then when there's a chance, after they burn off that energy, they will fall back to their original seats. And when it does this, it's going to give off this extra energy as light. That's why we did all of that stuff with light before. So when that energy comes off, when it expresses all of that energy, it shines, it does its thing, it gives off that energy as light, and it goes back to its seat. The amount of energy given off is dependent on the electrons and where they're falling back to, and that's going to determine the color of the light. And that is it. Everything that you just saw is something that we'll do in class. So this is it. Sorry for the longer video. Let us know if you have any questions, since I just tried to rush through this. Hopefully you remember some of this from honors. And peace, and have a good one.